All right, now let's come back. Let's come back to the class. Okay, in that session we talk about the Neyman Pearson. So the most fundamental idea is that we like to constrain this PFA and maximize PD. Mathematically, it's understandable, but the thing is, I like to remind you that it has very important engineering implications, which is, think about this, PFA is a error, right? It's some kind of error. And of course, we always like to we always like to uh, have small errors. So we constrain that error to a certain threshold and maximize the thing that we like. We like to have good PD, so we maximize it. But we don't like PFA, so we constrain it. Think of it this way, and that'll be easier. Okay, all right, and then let's take a look at the PFA. A PFA is equal to P decision on H1 condition. Uh, I like to just explain a little bit. This small thing of sort of like a semicolon. When it's used in this probability, we think of it as a conditional probability, which means that condition on H0 is the truth. Uh, I like to explain the concept truth, truth, right? Sometimes we call it ground truth, but truth is good enough. While the truth is H0, meaning that the real thing is H0, but we make a decision for H1. The real thing is H0, we make a decision for H1. When that happens, it's a PFA. And then we go into mathematics, condition on H0, the sample. Remember, recall that what I said. I say a realization and observation coming from a random variable. So while H0 is correct, not correct, while H0 is the truth, we call this. This is H0, right? This is H0. It will be distributed this way. But is it possible that we make a mistake? It is, because look at this, look at this. H1, H0, they all have distributions all over the horizon, all over the horizon. So as a result, no matter what the truth is, may it be H0, may it be H1, whatever it is, it it is always possible to have a sample anywhere on the horizon, right? From minus infinity to positive infinity. If you look at this, it's the same thing, except you have a different mean. You know, the distribution shifted a little bit, but it doesn't mean that its sample value is always large. No, it could be small. Okay, so uh, when we come back to this, it will be easier to understand this uh, hypothesis. And then, while under this hypothesis, when the sample is larger than gamma, then that's when we make a decision for H1. Right? That's when we make a decision for H1. And therefore, condition on H0, its probability distribution is like this. Right? It's like this. And then we will be integrate its probability from gamma to infinity. In other words, we are we're integrating which part? We're integrating this part. Look at my cursor. We're integrating this. It goes, it has tail with very small value, but it goes to infinity, indeed, because it's a Gaussian random variable. So it indeed goes to infinity. Okay, so we are going from gamma to infinity, and we are integrating this thing. We're integrating this thing, right? So as a result, we will have Gaussian distribution, and then it goes this way. Then it has Q of gamma. It has Q of gamma. Then, as an example, if we like the probability of false alarm to be 10 to the minus 3, we have gamma equal to 3. The question is, how do you find Q of gamma equal to 10 to the minus 3, and yet you get gamma equal to 3? I, 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 I have to explain this. It has to go through some trial, some trial, or you do numerical approach. If there is a class that's called numerical approaches, it will explain a lot of things, teaching you how to calculate non-closed form solutions. A lot of things that are non-closed form, and but you have to calculate it. Then there are various approaches, and numerical approach is one of them. So uh, I would say if you set Q of gamma equal to 10 to the minus 3, then gamma will be equal to 3. Okay. We will therefore decide H1 if x0 larger than 3. Okay. So if we take a look at this, it is actually very far away from the center. It will be threshold will be set here. Will be set here around 3. Then its probability of false alarm will be 10 to the minus 3. Then of course you will see large PB, right? The whole session is the whole area, the whole area. This whole area is a PD. So we like to have a PFA like this, and then we have a reasonably good PD. But this is not. This is just a case. Some people may come up and say he wants to have PFA 10 to the minus 4. Then you have a larger gamma and you have a larger PD. Okay. And therefore, with this choice, we have PD equal to something like this, and condition on PD, px0 larger than gamma, and then you do the calculation. Remember that this calculation is a Gaussian distribution with zero mean. This is a Gaussian distribution with mean equal to 1, right? Mean equal to 1. As a result, you are integrating a Gaussian distribution with mean equal to 1. And then it becomes Q of gamma minus 1, Q of 2, which is equal to this. Again, how do you get this? It's a numerical approach. It's numerical approach. Okay. Uh, in fact, those common random variables, they have various tools in the MATLAB, in the C packages, in the Python, and then if you just search on the internet, you will see people calculate that for you online. So not a big issue. Okay. So now here comes the question. The question arises as to whether PD is the maximum PD for this problem. Our choice of the detector that decides H1 if this is just a guess. Will there be a better approach, right? Mathematically, we like to maximize PD, but when you set this threshold and then start to get this as the PD, will we say that will we be able to say that PD is the maximum for this problem？所以大家了解问题吗？就是说，我们原本的问题是要 constrain 这个，然后 maximize PD。现在我们设了一个 threshold，然后把 PD 做这样的积分，然后我们就说，哦，我们得到了一个 PD，看起来好像蛮好的。但是数学上来讲，数学上来讲，这真的是最好的 PD 吗？这真的是最大的 PD 吗？因为我们要最大化 PD 嘛。好，那我先跟各位直接讲答案，是，这就是。那为什么是？这可以证明，这可以证明。但是呢，我们可以先暂时说，设学习后的方式，然后来算出来 constrain 一个 PFA，然后得到一个 PD，这就是最好的方式。所以最好就是 PD 最佳化、最大化这样子。好，那这个是数学上可以证明的，它只是说我们等一下看一下有没有证明的哈。好，那 let's come back to here. Decision region and probabilities. When you make a threshold, we make a threshold, then you have PFA, you have PD, because you are making a guess. When something is larger than PD, then you say that this is good. This is the PD that you like. So we up to this point, we have obtained a couple of things. The first thing is PFA is done, PD is done. Then decision region. This is also very important because in the engineering problem, this is what you want to have, right? You like to have a decision region give you when people give you a sample, let's say -1, you like to make a decision based on that sample. So you need decision region. Then this is a decide on H0, decide on H1. Okay, so we will say that this is a decision regions. Decision regions. Uh, so let's say R1. It's just a notation here. R1 is a notation, nothing serious. Okay, so uh, R1 be the set of values that map into decision H1. Decision H1. So we will say R1 is the X, the region of X that decides H1 or reject H0. Of course, there is only two hypotheses. So when we say reject H0, that means we decide H1. Okay, it's the same thing because we have two hypotheses. But if there are multiple hypotheses, then this would not be the case. 稍微慢一点，然后让同学可以跟上一下进度。我们在64页 ，We are at page 64. Okay. So that's called the critical region. The set of points in Rn that map into a decision H0 is a complement of R1, or we say R0. Complement 就是互补的那个嘛，互补的对，成对的对嘛，互补的那一对。那当然，整个实数线只有两个 hypothesis 嘛，所以不是 R1 就是 R0 啊，对不对哈？So R0 is to decide H0 or reject H1. Then clearly R0 union R1 is the Rn. So that's I think that's reasonable because the whole thing needs to be R1 or R0. 我们必须要强调一点是说，在整个 sample 的 domain 里面，每一点都必须被 define。 也就是说每一点它必须有一个 decision，你不能说没有 decision，没有 decision 在的这个方法在 detection 的问题里面，代表你这个方法是不对的，是有缺陷的。哦，譬如说我们举例来讲，你现在有一个 BPSK，然后你收到一个讯号，就像那个就算那个讯号很烂，再怎么品质不好，你都不能说我不决定零或一，对不对？在数位通讯系统里面，你必须要决定零或一，就算那个讯号的品质再怎么不好，你都必须要决定。Okay, so this is the same thing here. You always have to decide which hypothesis it is. So R1 and R0 will compose of the whole domain, the whole domain. 全这个realization 的 domain 必须一定要属于某一个 hypothesis，不能没有属于这样子。Okay, so so let's sort of the data space. It calls data space. You like to call it sample space, or you like to call it the domain of the horizon, whatever you call it. You know what it means. We need to define the domain into different regions. Okay, so uh, the PFA then becomes PFA equal to condition H0, conditional H0, then probability density function of X conditional 0, and then we integrate with respect to X for the R1 equal to alpha. In other words, if it's for this figure, we are integrating this. See my cursor here. We are integrating this. Okay. And then in statistics, alpha is termed the significance level or size of the test. Alright, significance level. Now there are many sets of R1 that satisfies 3.2. Our goal is to choose the one that maximizes PD. Okay, you do the integration for R1, and then that is the R1 under H1, the probability density function of X under H1, and you do the integration for X, and with respect to R1. Then PD is called the power of the test, and it's a critical region that attains the maximum power, the best critical region. The NP, this is Neyman-Pearson. The Neyman-Pearson theorem tells us how to choose R1 if we are given this, and this. Alright. Alright, so now we are at page 65. 65. Okay. Okay, so uh, here are some statistical terms for hypothesis test. For example, H0 we call no hypothesis. Test statistic and threshold we call it detector. Engineers we call it detector. No hypothesis. Alternative hypothesis for H1. Then that's a signal plus noise hypothesis. Signal present decision region. And false alarm. And it calls, as I said, it calls type 1 error, but we call it false alarm. Type 2 error, as I said, it's a misdetection. You miss the target. Then it's the level of significance, probability of false alarm, probability of type 2 error, probability of miss, power of test at 1 minus beta. we call it probability of detection. Just be familiar with those terminologies because we will use it from time to time. So now we formally define the Neyman-Pearson. This is formal definition. So we maximize PD for a given PFA. We are given a PFA. So that simple sentence would define this Neyman-Pearson criteria. Then all the rest is mathematics. All right, it's mathematics. Mathematics as a tool to achieve our engineering goal. Okay, so we decide H1 if L, well, this L is in fact the likelihood ratio, but I'll just use the function L to say it, but in fact, sometimes we call it likelihood ratio here, likelihood ratio. Okay, so this Lx is a function of a sample equal to probability of X condition on H1 over probability of X condition on H0 larger than gamma, larger than gamma. This is the, in fact, this requires a rigorous proof, but we are not going to do it. Okay, we will just say the likelihood ratio is defined this way. And when we set a threshold on the likelihood ratio, and then we come up with a decision region. That decision region will help us to do H1 decision. And of course, then the other part will be H0 decision, right? H0 decision. Then the alpha, no, the threshold gamma is found from PFA equal to this. And then for what? For P of X conditional H0 D of dx. And then you do the integration from X for X. Then X is likelihood ratio larger than gamma. And we set that to alpha. When we set that to alpha, then you will find an area for H1 and an area for H0. And that help us to do the decisions. And then that will help us to maximize PD for given PFA. And we call it Neyman-Pearson. We call it Neyman-Pearson. Okay, so the next thing is we are going to do a simple example, but we will stop it for a moment and come back later.